Quantum computing simply explained. What is quantum computing? Quantum computing harnesses the principles of quantum mechanics to process information. Unlike classical computers that use bits, zeros and ones, quantum computers use quantum bits or qubits. These qubits can exist in multiple states simultaneously, a phenomenon called superposition. Think of a coin. A classical bit is like a coin that's either heads or tails. A qubit is like a spinning coin. It's both heads and tails until you stop it and look. This ability to be in multiple states at once is what gives quantum computers their power. But there's more. Qubits can also be entangled, meaning the state of one qubit is directly related to the state of another, no matter how far apart they are. This allows quantum computers to process vast amounts of information simultaneously. The building blocks qubits. Qubits are the fundamental units of quantum information, typically made from subatomic particles like electrons or photons. Creating and maintaining qubits is challenging due to their incredible sensitivity to their environment. Several methods exist for making qubits. IBM and Google use superconducting circuits, loops of superconducting material cooled to near absolute zero. IonQ and Honeywell opt for trapped ions, which are charged atoms held in place by electromagnetic fields. Some researchers are exploring silicon quantum dots. Similar to transistors in classical computers, but operating at the quantum level, Microsoft is pursuing a different approach with topological qubits, using exotic quantum states of matter. Each method has its strengths and weaknesses. Superconducting qubits offer speed, but are prone to errors. Trapped ions boast better stability, but operate more slowly. The quest to create the ideal qubits for practical quantum computers is ongoing, with each approach vying for supremacy in the quantum race. Quantum gates, the logic of quantum circuits. Quantum computers rely on quantum gates to manipulate qubits and perform calculations, much like classical computers use logic gates. The Hadamard gate is crucial for creating superposition, allowing a qubit to exist in multiple states simultaneously. The Sianot gate plays a vital role in entangling two qubits, enabling them to interact in ways that classical bits cannot. The Poly-X gate serves a similar function to the classical NOT gate, flipping a qubit's state. Quantum algorithms are constructed by combining these gates in specific sequences. The challenge lies in designing algorithms that leverage quantum properties while minimizing errors. This delicate balance is at the heart of quantum algorithm design, requiring a deep understanding of both quantum mechanics and computer science. Quantum supremacy, a milestone achieved. In 2019, Google made headlines by claiming to have achieved quantum supremacy. Their 53-qubit Sycamore processor completed a specific calculation in just 200 seconds, a task that would have taken the world's fastest supercomputer an estimated 10,000 years. This achievement, while significant, doesn't mean quantum computers are ready to replace classical ones for everyday tasks. The calculation was carefully chosen to showcase quantum advantages and has limited practical applications. For most real-world problems, classical computers still hold the upper hand. However, Google's demonstration ignited a spark in the quantum computing field. It proved the potential of quantum systems and catalyzed increased investment in research. The race to develop practical quantum computers has intensified, with tech giants and startups alike vying to push the boundaries of what's possible in the quantum realm. Error correction, the quantum Achilles heel. Error correction stands as one of the most formidable challenges in quantum computing. Qubits are extraordinarily sensitive. Even the slightest disturbance can introduce errors, potentially derailing calculations. While classical computers use relatively simple error correction techniques like parity checks, quantum error correction is a far more complex beast. The leading approach, known as surface code error correction, arranges qubits in a two-dimensional grid and employs sophisticated algorithms to detect and correct errors. However, this method comes with a steep cost. It requires a large number of physical qubits to create a single, reliable, logical qubit. Estimates suggest that anywhere from 1,000 to 10,000 physical qubits may be needed for each logical qubit. This need for extensive error correction explains why we're aiming for millions of qubits in practical quantum computers, even though theoretically only a few hundred are needed for useful calculations. It's a reminder of the vast gulf between the elegant theory of quantum computing and the messy reality of building these machines. Quantum algorithms, where quantum shines. Certain problems are tailor-made for quantum computing, showcasing the potential to revolutionize fields from cryptography to drug discovery. Shor's algorithm, for instance, can factor factor large numbers exponentially faster than classical computers, posing a significant threat to current encryption methods. Grover's algorithm offers a quadratic speedup for searching unsorted databases, a capability with wide-ranging applications in data analysis and optimization. Quantum simulation stands out as a particularly promising application, allowing us to model complex quantum systems with unprecedented accuracy. This could accelerate the development of new materials and drugs by simulating molecular interactions at the quantum level. In the realm of optimization, quantum computers show potential for tackling problems that involve finding the best solution among countless possibilities, a capability that could transform industries from finance to logistics. These algorithms are just the tip of the iceberg. As our understanding of quantum computing grows, so too does the list of problems where quantum approaches offer significant advantages over classical methods. The quantum ecosystem. Building a quantum computer involves far more than just assembling qubits and gates. It requires a complex ecosystem of supporting technologies and expertise. Cryogenics plays a crucial role, as many quantum computers need to operate at temperatures colder than outer space to maintain qubit coherence. Precise control electronics are essential for manipulating qubits with exquisite timing and accuracy. On the software side, a sophisticated stack is needed to translate high-level quantum algorithms into the low-level operations that control individual qubits. Error mitigation techniques are crucial for extracting useful results from today's noisy quantum hardware. Companies like IBM and Google are taking a holistic approach, developing full-stack quantum systems that span from hardware to cloud-based quantum services. This integrated approach allows them to optimize the entire system, from the physical qubits all the way up to the user interface. The quantum ecosystem extends beyond just the tech giants. A growing network of startups, academic institutions, and government laboratories are contributing to various aspects of quantum technology development. This collaborative effort is crucial for overcoming the multifaceted challenges of building practical quantum computers. Quantum classical hybrid approaches. While we await the arrival of large-scale quantum computers, hybrid quantum classical approaches are gaining traction. These methods leverage the strengths of both quantum and classical computing, using quantum systems for specific subroutines within larger classical algorithms. The variational quantum eigensolver, VQ, exemplifies this hybrid approach. Used in quantum chemistry, VQE combines a quantum circuit with classical optimization to find ground state energies of molecules. This allows researchers to tackle problems that are beyond the reach of purely classical methods, even with today's limited quantum resources. Quantum machine learning. The intersection of quantum computing and machine learning is a hotbed of research, promising to push the boundaries of both fields. Quantum versions of classical machine learning algorithms are being developed, including quantum support vector machines, quantum principal component analysis, and quantum neural networks. These quantum machine learning approaches could potentially process certain types of data much faster than their classical counterparts. For instance, quantum principal component analysis might dramatically speed up the process of finding patterns in high-dimensional data, a common task in fields like image recognition and financial modeling. However, significant challenges remain. Data input and output pose a major bottleneck. Loading classical data into a quantum system and extracting useful results can be time-consuming, potentially negating any quantum speedup. Moreover, proving quantum advantages for real-world machine learning problems is not straightforward, as classical algorithms continue to improve rapidly. Quantum sensing beyond computing. Quantum technologies extend far beyond just computing, with quantum sensing emerging as a promising near-term application. These sensors leverage quantum effects to measure physical quantities with unprecedented precision, opening up new possibilities in various fields. Atomic clocks, which use the quantum states of atoms to keep time, have already revolutionized global positioning systems and could enable new forms of navigation. Quantum magnetometers can detect tiny magnetic fields, finding applications in medical imaging for brain activity mapping and in geological surveys for mineral exploration. Quantum gravity sensors, still in early development, could transform underground mapping. They might allow us to detect underground caves or mineral deposits without drilling, or improve our ability to predict volcanic eruptions. Quantum communication, unbreakable encryption. Quantum key distribution, QKD, represents a paradigm shift in secure communication. By using quantum properties to create encryption keys, QKD promises unbreakable encryption. Any attempt to intercept the key disturbs the quantum state, immediately alerting the users to the breach. China has taken a lead in this field, launching a quantum communications satellite that has demonstrated intercontinental QKD. This milestone hints at a future where quantum-secured global communications are a reality. However, challenges remain in creating quantum repeaters for long-distance quantum networks. These devices necessary for extending quantum communications over large distances are still in the early stages of development. Overcoming this hurdle is crucial for realizing the full potential of quantum communication networks.